Okay, got it. Now well, but I can still make propaganda. So Poisson 2022. We had this problem that Poisson 20. Okay, let me share a screen. Look. Okay, you can share. Well, that's our beautiful poster, which is a fish. So Poisson dancing flamenco. This is the poster of the event. And this is going to run more or less from May, officially from April, but probably most activities will start in May until October. And it's going to be something happening between Barcelona and Madrid. We have a school, okay, which is going to happen in Barcelona. So this is a good occasion. If we can all travel next summer, that we are all looking forward, this is a good occasion to visit in the summer Spain. And so we start, like, I want to highlight that we have we have a list of activities, but let's say that the classical activities are the Poisson Advanced School that will happen in Barcelona, okay? And here we have wonderful posters. That's what we have so far. This is good. So we have speakers for the school are going to be Ana Balibanu, Enrique Burstin, a course on singular foliation, so very appropriate if you are following this course, of Camilo Angengu, and a course on index theory of Lie algebra, of Lie groupoids, this is missing in the title, by Eric Banner. So we are going, I mean, we still didn't open the registration process, but it will be open soon. And we plan to have quite a lot of grants for students, okay? These grants probably will only be able to cover registration fee and accommodation, but it's something that can help you, okay? So this should be open maybe in a couple of months, but keep your eyes, well, I'll put a link of this in my webpage so you can register. And then we have like the main activity is going to be, one second, I have to move this. The main activity is going to be the conference, and the conference will take place in Madrid, okay, in the center of Madrid, because, well, the main research center in Madrid is outside of Madrid, but we will do it in the center. So you have your free time to visit museums and etc. Okay. And well, so far we still don't have here more information, but okay, since you are connected, I can tell you that, for instance, one of our speakers is going to be Honglei Lang, who is connected here. So it's a pleasure to already say this as a spoiler, that she will be one of our speakers. So this is good. This is perfect. We will keep on updating these websites with information about speakers and so on. Still, well, I mean, the website of the school is in Madrid. Wait, we need to link it. We didn't link it. Now I realize that I need to correct this. Well, it's in Madrid, and this is the advanced school, but there is another website in Madrid. I'll project it next time because it's not linked to CRM, but it should. Okay. Well, it's linked here to the beginning. Maybe I can find it. Here. Well, still, if you look for it, you can still find it. Though we will have, for instance, we plan to have an activity on generalized geometry. This is good for Raju, and this will happen in Madrid in June. Okay. Then yeah, we have here the link. Oh no, it's not what it's. No, it's correct. This is the link. That's the link. Sorry, that's in ICMAT. Is the correct link, but still we didn't disclose the information. Okay, but we have very interested speakers who have already accepted. Well, I say Honglei Lang, she will accept today, I hope. We also have Kolia Resetikin, Marco Galtieri, etc. So I think that this is a very interesting course for people. Anton Alexeyev is also going to be one of the speakers. it's a very interesting activity for the ones who are here. So keep your eyes open because we plan to have this kind of grants that allow you to go there. And then it's a good occasion to visit Spain, okay, talking about the weather. So now let me go back. I think we have 31 participants, but okay, this is the third day. Maybe people got tired. So I think we can start, right? Chung, what do you think?
Yeah, I think maybe we can start.
Yeah, we can start. Okay. So what? I keep on updating the website, okay, with the information. So now you can already find here. Do we have an update of the list of problems, Pau? Because I saw you updated the file, but I think that you added the solutions, no? I don't need to hang it on the website, or should I?
Yes, we will. With respect to the last version you have, we added one extra problem, one starting problem, but it's and it's since the document is with the solutions, we will again make two versions of it, one with the solutions, another one without the solutions, and we will post today the one with the extra exercise without the solutions.
Okay.
And then after Thursday, we will post it with the solutions.
Okay, perfect. It's a very ambitious program, the one we have for Thursday, but we already got people who did the exercises and are planning to be volunteers. If you have done the exercises for this Thursday and you want to go on this whiteboard, virtual whiteboard, let's say, that you want to share the screen and show everyone how you solve the exercise, maybe it's a good idea that you tell Pau in advance, because he will organize he will assign different, so I don't know, if two people have done the same problem, he will decide who is going to the whiteboard. I already got some emails of people who are trying hard and are getting exercises. So I don't know, Pablo, he's around, I think. Pablo is one of them, but he's not the only one. So just to avoid collapse and two people doing the same exercise, well, I mean, you have to try to do all the exercises, but if you want to go and try to show everyone, then the best is that you send an email to Pau, let's say no later than tomorrow. Okay, so Pau organizes the schedule of who goes out and so on, and then we will provide. I think that the list of problems is very ambitious, but we will have a new list for the other programs. Okay, here I posted you have the links if you missed some of the previous talks, and these links are via Zoom. I plan to post them on my YouTube channel, so you have all of them and it's easy to find, but still I didn't have time, so sorry. So let's go to the slides of day 3. You can open them if you missed one of the classes, because I keep on, I have a plan, of course, on the slides, and then I skip the plan. That's a standard. Okay. Well, more or less I follow the plan, but then I do some annotated slides because I prove some results on the slides. So I keep on putting the slides here. So you can recover the slides with annotations and without annotations if you couldn't follow the last class. So still it's okay. Okay, perfect. So let's go. And now I'm going to stop sharing here. And I'm going to start sharing with the computer. In the meanwhile, if there are some questions that somebody wants to ask, this is a good occasion that you can unmute yourself and ask questions. Okay, to share screen. In the meanwhile, are there any questions from last class that you want to? No. Okay, sorry, it's going to take me 1 minute because Zoom is updating the plugin to share with the iPad. Sorry. Okay, there we go. We are here. Okay, good. Well, it was pretty quick. Okay, now there we go. Good. Okay, perfect. Notes. Wait, what happened with my notes? 1 second. I thought that I had, sorry, I'm talking to myself. Okay, well, I need to do something. I had my slides here already prepared. Okay, yeah, they are here. No, these are the other ones. Okay, well, 1 second. 1 second. These are my other slides. Let me enter my web page. Okay, these are slides of day 3, and I had added these to the notes. I don't know what I did. Wow. Okay. Download. No. Wait, now I have a problem, which is that it's not downloading this, no? Go there. One second. With this, I cannot write. Can I write? No. Sorry, I made a mess with my computer. I had the script, the slabs here. Okay, everyone is going to boom, boom. Everyone is looking at my email, but it's not problematic. I have too many emails. This is something I sent to myself yesterday night. Yesterday night to myself. Sent. Sorry. Sorry, everyone is looking at my, this is not very interesting, but I have a strong activity of emails. I had a direct link to my slides that, 1 second. Okay. Let me do something. I stopped sharing. Sorry for this. That I hide my slides here, but I didn't share them as notes, so I need to download them. And I had a direct link. Oh, wait. Oh, it's true. I didn't do this. Okay. Okay, 1 second. 1 second. 1 second. Okay, in the meanwhile, you can start yourself to look at the slides. I am just trying to download this. And I mean, what I'm going to do is to send me an email from my Dropbox, because for some reason it doesn't download from the website. And on 3.3. I send this to myself. Sorry for this. Oh, what's going on? Didn't you send this email, computer? Okay, what the hell? Books, inbox. Says that I have a problem with my, okay, there we go. It's very slow. Do you hear me correctly today? Because it seems that my internet connection with my iPad is sort of slow for the first time.
We hear you clearly.
Okay.
We can see you and hear you correctly, I think. Yeah.
Okay, good. Then it's something to go with my iPad. I'm sorry. I'm going to, it's here. Okay, it's here. And now I'm going to share. I mean, sorry, because I did this just to save this. So now I'm gonna share. Sorry for this interruption, technical interruption, because this is my computer. For once, my computer is slower than I am. So let's share again. It took a while, the pad, to get the email with this. Share. I assume. Good. Well, I hope that it's just slow now. I'm telling everyone how good was the iPad and how happy I was about my iPad. And I hope that's the case. Okay, here are the slides. Sorry for this story interruption. Well, in the middle, we got 2 more followers of the course, so this is good. Okay, remember that, what did we see the last day? Okay, we wanted really to get to the point of understanding these singular symplectic structures. So far, we understood them as Poisson structures. And the other day, I was explaining things in Poisson geometry that we were going to need. I mean, of course, Poisson geometry is a big world, and I could spend at least 1 more session there, but we need to go on. There is just one notion that I'm going to need today from Poisson geometry. And this is the first notion here of the first slide, which is the notion of modular vector field. Okay, that's the last brick on the wall that I need from Poisson geometry. And the definition of modular vector field for a general Poisson manifold, it's a bit complicated. By the way, Pau, maybe it would be good that not for this session of Thursday, but for the other one, we put some problems of computation of modular vector field. I think this is good. We will think about this.
Yeah, we can do it. I think we can do it. And
this afternoon in our meeting, we can. This is a good thing, just to remind myself. Because in general, if we have a Poisson manifold, it's quite a complicated thing to compute. Indeed, this was introduced by Alan Weinstein in his famous paper in 1988. So if you think about it, these dates are quite recent, okay? And this has to do with the following idea, before I explain the definition. If we have a symplectic manifold, we know that Hamiltonian vector fields are going to preserve the symplectic form. And thus, what is called the symplectic volume, which is that if you are in a manifold of dimension 2n, and your symplectic form, you can look at it as an area form if you are in dimension 2, okay? If you are in dimension 2, if you're in dimension 2n, in order to get a volume from your symplectic structure, you need to wedge it n times, okay? I don't know if I have here a space for, I left quite a lot of space for notes here. Space for notes. What I say is that, remember that in symplectic geometry, okay, when we have a symplectic form, okay, this is a symplectic form. We can have like 2 situations essentially. If the dimension of your manifold is 2, then omega is an area form. And you can think of an area form already as a volume form, because we say it's a top form on your manifold. It's a volume form. Okay, okay. If we go to dimension 2n, we need to make more. we need to consider, we need to take our symplectic form, which is a 2 form. And if we want to get a volume form, we need to wedge it how many times? If I wedge it once, I have a form. So I need to go and wedge it. If the dimension of my manifold is 2n, I need to wedge this n times. Then I have omega n. And omega n is usually known as symplectic volume. Symplectic volume is important in symplectic geometry. For instance, if we want to prove something like Henan theorem that we will not cover in this course, but this would be another interesting thing to consider about symplectic manifolds. Then there is something that goes on in the symplectic business, which is the following. And that's something that it's peculiar from symplectic geometry. If I take a Hamiltonian vector field, then, of course, this Hamiltonian vector field, which satisfies, remember, this equation in symplectic geometry, by definition, by this very definition and Cartan formula, this is an exercise in symplectic geometry, we know that the Lie derivative of this is 0. This means that, of course, a Hamiltonian vector field preserves the symplectic form. This is to say a Hamiltonian vector field is a symplectic vector field. In particular, is a Poisson vector field. But what's interesting, and that makes it a bit different from general Poisson, is that it also preserves, just from standard Leibniz formula, the symplectic volume. Therefore, if we want to compare how far is our Poisson manifold from a symplectic manifold, a good way to compare it is to see how the symplectic flow of the Hamiltonian vector fields, how, if I take in general for a Poisson manifold, if I have a volume form, then this volume form cannot have a direct relation like this unless it's already symplectic from time 0. So the following definition, due to Alan Weinstein, wants to control how the flow of Hamiltonian vector fields change a volume form. That's the motivation. And we know that in the case of symplectic manifolds, as we can take as volume the symplectic volume, the answer is that it doesn't change it. Okay, this is why symplectic manifolds are unimodular, meaning that this vector field is 0. So what is the modular vector field? The modular vector field is a vector field that, and Pablo Nicolas, who is connected, is going to adore this. It's a vector field that we define in an intrinsic way. We define it as a derivation, okay? We say that we take now any function here, take any function of your manifold, and now what I do is to see how, if I have a volume on my manifold, which is not necessarily a symplectic volume because my manifold is Poisson, okay? I want to see how the Hamiltonian vector field changes this volume. And how do I do it? I compare this Lie derivative, okay, together with omega. And this mapping here defines a derivation. And therefore we know that whenever we have a derivation, what we have in front of us is a vector field, okay? Then this definition looks a little bit abstract, but when we do the session of problems that will not be, this will be dealt in the last session of problems, we will see that it's easy to compute because here you can express your vector field in some local coordinates, and then you take as function the local coordinates, and therefore this is going to give you the coefficients of the vector fields in this local basis. So that's going to be the way to compute it. Well, important properties about the modular vector field. One thing is the Hamiltonian vector field, and the other thing is the modular vector field. Notation can be improved, okay? But notation, of course, this vector field depends on the Poisson structure. This is why we put Poisson, and depends initially on the volume. Though we will see that this dependence is apparent in the sense that the topology behind it's going to be exactly the same. Okay. So this first condition tells you that the modular vector field preserves the Poisson structure. This means that it's a Poisson vector field. And it also preserves the volume form. That's easy to check. Observe, don't get confused with the fact that in symplectic geometry, Hamiltonian vector fields preserve the volume. This vector field is not going to be Hamiltonian in general. It's going to be a new class of vector field, the modular vector field. Indeed, as it satisfies this condition that it's a Poisson vector field, what happens indeed is that we may ask if there is some kind of intrinsic, the definition already of modular vector field is intrinsic, if there is some kind of intrinsic definition. Indeed, the other day, I went to explain many things in Poisson geometry. I went over the line of what I wanted to explain, but now I'm glad, because one thing I said is that there is something called Poisson cohomology, okay? And that Poisson cohomology you define just on multivector fields by taking the bracket with the Schouten bracket, okay? And of course, we are not going to be able to consider Poisson cohomology in general for a general manifold. It's very difficult to compute. Today, I'm glad to tell you that we will be able to tell you what is the Poisson cohomology of a B-Poisson manifold. And it's going to be very easy to compute in some cases. Poisson cohomology of a symplectic manifold is just the ramp cohomology, for instance. Okay, what happens, one can see that what is really the dependence here. I say that the modular vector field depends on this, even in notation. Here I put that it depends on the volume form. But the question is, how much it depends on this volume form? If I have another volume form, because these two forms are top forms, the new form can only be H omega, can be a multiple of the first form. Then a simple computation allows you to see how the modular vector field changes. Here we assume that the Poisson structure is the same. That's why we don't put it. And the conclusion is that the difference between the modular vector field, if you fix one volume form or the other, is a Hamiltonian vector field. Okay? What does it mean? This means that the first cohomology class that I can now tell you, even if we didn't do a lot of things, of my Poisson manifold, is just the quotient of Poisson vector fields modulo Hamiltonian vector fields. In the case of a symplectic manifold, this is exactly going to be the quotient of symplectic vector fields with Hamiltonian vector fields, okay? And this is going to be easily identified with the rank cohomology group. As this is something that you all know already by now, that the obstructions for a symplectic manifold vector field to be Hamiltonian live in H1 in the first cohomology, the RAM group of the manifold. The obstructions for a Poisson vector field to be Hamiltonian lives also in the first cohomology group, but of a different cohomology. This is the Poisson cohomology, okay? So this means that even if this vector field, the definition depends on the volume form, indeed, the class that this vector field defines in cohomology doesn't depend on this volume form and just depends on the Poisson structure. Therefore, it makes sense, for instance, to talk about manifolds with zero modular class. These are called unimodular. And as I already explained, symplectic manifolds are unimodular, but they are not the only ones. The manifolds we saw in last session, could I mention one symplectic foliations where you have a Poisson vector field transverse to it, which is a class that we widely discussed last class, are also unimodular. And this is going to be another problem in the second list. And in the case of B-Poisson manifolds, that imagine that I take that the bracket is of this type. This means when I use this notation, remember I can recover the bivector field already in this formula. And from the bivector field, I can recover, and this is something that I cannot do in general for any Poisson structure, of course. This is something I can do for B Poisson. I can dualize, and then I have this form. Why? Sorry. Y dx dy. Okay, and this is going to be what we call the dual. So if you have this Poisson structure, okay. Now, as I said, and this is going to be a problem in the list, but this is an easy problem with this definition, because then you can take some local, you know that the Poisson structure writes like this, and you can check what is the image of the functions x and y. As we know that this is a derivation, this gives you the coefficients of the vector field. And this is an easy exercise, but we will do it, that the modular vector field, when the critical set is y, given by y, is given by the other one. This is partial of x is going to be the modular vector field. And in general, this not only works in dimension 2, but it works in any dimension. And that's something interesting, that for B symplectic manifolds, the modular vector field is not 0, okay? But for the restriction of the Poisson structure defined by a B Poisson structure on Z, the modular vector field is 0. That's an interesting observation, okay? This modular vector field, of course, when you restrict to Z, you have like 2 Poisson structures, the induced one on Z, okay, and the ambient one, okay? And an interesting thing, when I talk about the modular vector field in B Poisson, I mean already this modular vector field. So if I make a picture in this of this, I could try to make a picture, okay? This could be, for instance, the sphere, but it's higher dimensional. Observe that the situation is the following. We have y equal to 0, y1 equal to 0, and that's an hypersurface. And that's the critical hypersurface that the other day I called a Z. And on Z, we have an induced Poisson structure, which I can compute easily, because when I just replace y1 by 0, the Poisson structure is this one, which I know it had to be a constant rank Poisson structure. And that's the expression of the structure that I have. Okay, so this is some. My writing is a bit bad because I'm left-handed and I cannot put my elbow on the table. That's a complication that I have for being out. I don't know if more left-handed people have this problem. Okay, so this is the sum. Let me do a better writing of xi wedge partial y. If you want this Poisson structure, I cannot say it's symplectic, okay? Because the manifold has dimension 2 and -1. It cannot be symplectic, but it's a Poisson structure of maximal rank, and this defines a foliation on codimension 1, and this foliation is precisely given by xi x1 equal to constant. For each value of x1, I get a symplectic leaf. Now I want you to understand what is the meaning of the modular vector field. Okay, maybe it's good that now.
Sorry, Eva. Can I just ask a question regarding
Yes,
the definition? So in the definition, you said that given a f, you will map it to the derivative of xf, which is a Hamiltonian vector field of f applied to this volume form over this volume form. So this somehow is a measure like how much percentage this volume form has changed according to the Hamiltonian
Exactly.
f, right? So due to the fact that volume form has essentially only one how to say that there is essentially only one volume form up to a function. So this actually gives you another function, right?
Exactly. This is what I was explaining here let me highlight this here.
Mm.
This is what I was explaining here. If I have two different, I mean, how does this depend on the volume form? If I have two different volume forms, the difference is multiplication by a function, as you mentioned.
Yes.
And then you compute, and then the funny thing is that when you compute the modular vector field with this new omega prime, the difference is a Hamiltonian vector field.
Okay.
Therefore, it does not depend so much on the volume form. Why? Because, okay, it depends because you have this other term. It's not the same vector field. But in cohomology, this vector field is a Poisson vector field. Therefore, I can take class in Poisson cohomology. It's class in Poisson cohomology, which is something that the other day I was very quick, and I say that it's possible to define this cohomology. Maybe this could be an exercise in the list. Now Pau is getting his hairs up because he's thinking, I have to do all these exercises. Okay, so this could be an exercise in the next list to check that if I have a vector field which is closed, it defines what would be the analog of cocycle in this cohomology. Okay, it's a cohomology where instead of taking instead of taking forms, you take multi-vector fields. And if you apply it to a one vector field, okay, the condition that it's a cocycle, it's equivalent to being Poisson. Okay. Therefore, the first cohomology group is the quotient of Poisson vector fields modulo Hamiltonian vector fields. This means, summarizing, that if I change the volume form, these only change, the vector field is different, but its class in the first cohomology group of the Poisson manifold is the same.
I see. Okay.
So in a sense, this vector field has some kind of intrinsic definition. So it does not depend. So the definition, the vector field does depend on the volume form, but not its cohomology class in Poisson cohomology. And the cohomology class is what you call the modular class of the. That's why when you say modular class, and this is also related, and I will not get into this, to the modular class in number theory. There is a link to this. Okay, the modular class is the class of a pi in H1. Okay, well, that's the class of pi, no, sorry, of X, of the vector field, of the modular vector field, which we denoted as X super omega sub pi. That's this class. That's what is called the modular class of the Poisson manifold.
This is the definition of the modular class, right?
And as you observe, so in the symplectic case, as Hamiltonian vector fields, of course, preserve the volume form.
Yes.
Okay, preserve one, but now we know the trick. If it preserves one, it's okay. It doesn't matter because this means that the class in the first cohomology class is going to be 0. Therefore, the modular class of a symplectic manifold is 0. And the modular class of a codimension 1 symplectic foliation admitting a transverse vector field is 0. Okay, and that's going to be an exercise in the list, but it's easy to check. This connects to this codimension 1 symplectic foliation I was talking here. In the B symplectic case, the modular class is not 0, but I was in a magic moment, which is I was going to make the picture of this vector field. As this foliation is given by x1 equal to constant, the vector field partial of x1 is transverse to the symplectic foliation. So, and this vector field is a Poisson vector field, which is transverse to the symplectic foliation. Okay, this means that this is the Poisson vector field transverse to the symplectic foliation. When I was talking about what is the Poisson structure induced on the critical set, the conclusion is that this Poisson structure induced on the critical set is just the one that I was described in that simple example where I had a codimension 1 foliation admitting a transverse Poisson vector field. And this transverse Poisson vector field, you can always think, is the modular vector field of the ambient Poisson structure.
Okay.
Okay.
Okay. Yeah.
So, I mean, of course, here I open the door again, I opened the door to a theory that I could spend a lot of time in. I could discuss in detail Poisson cohomology. I'm going to leave it at least the H1, the first cohomology group, as an exercise in the next list. But of course, this is a fascinating work. I mean, there are books called Poisson cohomology. So this is a subject in which Poisson people have been working on, because it's very complicated to compute this cohomology in general, the Poisson cohomology. Good news that for our little guys, the B Poisson, this is easy. And that's going to be a little bit the message. And here, is it clear now, Chung?
Yes, it's much better now. Mm-hmm.
Thank you for the question. Any more questions that you want to ask? You have questions in the chat. Let me see if I can read it. Okay. No, no questions. So,
Eva, I have a question. Under symplectic reduction, does the modular class changes or they remain same?
Well, the thing is, okay, under symplectic, now you said the word symplectic reduction. You are condemning yourself forever to being in a symplectic manifold. Okay.
Okay.
So, and the thing is that if you are in a symplectic manifold, the good news, okay, or the bad news if you want, because this means that it's more boring, is that the modular class is 0. So the answer is yes. If I start with a symplectic manifold, the modular class is 0. If I do reduction, I get a smaller manifold of a smaller dimension 2n minus twice the dimension of the group I'm reducing, and then this manifold is again symplectic. Therefore, its modular class is 0. And your question makes a lot of sense. What happens? Do you have an analog of reduction? And that's a very interesting question. Do you have an analog of Marsden-Weinstein reduction on a Poisson manifold? This question makes a lot of sense. Okay, and there are ways to reduce Poisson manifolds. Okay, you can find many reduction, but in order to get a theory that works as well, what did I do? Just in order not to, okay. In order not to stop, because my iPad was stopping, I was touching it, make a mess. So what I'm saying is that the question that Raju is asking is very interesting, because the real question is, can you define Marsden-Weinstein reduction for any Poisson manifold? There is a way to reduce, but it's not going to be as nice as a Marsden-Weinstein reduction, as the one you want. However, for B symplectic manifolds, it's possible to define this reduction. Okay, and what I'm going to explain you now, it's on a spoiler of a paper that we are still writing. Okay, and the spoiler is that you can start with a B symplectic manifold and get a reduction which is automatically symplectic. This means that for B symplectic manifolds, the modular class is not preserved until reduction and under reduction.
Okay,
and there is a reason for that. That the kind when we consider, and this is a topic that is fascinating. Of course, I will cover the topic of Hamiltonian actions, what we call B Hamiltonian actions on BM symplectic manifolds. Okay, this is something that I will cover, and then we will see that there is a normal form. And the magic thing is that the first term of the normal form is going to be a function which is a logarithm, which is a function that in principle is forbidden because it's not smooth, but we will make some sense out of it. And the Hamiltonian vector field of this function, which is not smooth, cannot be considered as a Hamiltonian vector field. The Hamiltonian vector field of the logarithm is going to be precisely the modular vector field. And that's why when we can reduce by this modular vector field, what we are doing with our B symplectic manifold is killing the singularity and getting a regular symplectic manifold. Okay, this is something that you can more or less see in our old papers with Jonathan, but we decided to write this down in an elegant way with Anastasia, that I don't know if she's connected today because she had some internet connection problems. And this is something that we are writing down. So I have counterexamples to this question if you go out of the symplectic business. Okay.
Thank you.
So yeah, there are very interesting things going on. Now I wanted to comment this, because this is what I explained the other day when I explained things in Poisson geometry. What did I consider about B Poisson? We saw examples that we will see again on Thursday. They are going to be problems. I think it's good to do these problems, because otherwise you don't realize who are the main characters of your story. Okay, so what we saw is that this V Poisson structure induces a regular co-rank 1 Poisson structure on Z, this codimension 1 symplectic foliation. And now there are reasonable questions. One of them is, now imagine that I have a codimension 1 symplectic structure which this transverse Poisson vector. A natural question is, can I extend globally this to a B Poisson structure in a neighborhood of the manifold? Can I go from this model on Z to B symplectic manifold? That's a very natural question. And the answer is yes. But this codimension 1 foliation has to have the condition equivalent to having this transverse vector field. And this is something that has been known in the literature under different names. But I'm going to use the most common, well-known name, which is the one, I want to change the color, of cosymplectic manifold. Cosymplectic manifold appears naturally in several theories, including Keller theory, including Riemannian manifolds. It's a common land. Cosymplectic manifold is given by two forms, alpha and beta. Okay, alpha is a one form that I can choose to be closed, and beta is a two form that defines a symplectic form on each leaf. And these are forms defined on Z. This is equivalent, totally equivalent to taking a codimension 1 foliation admitting a transverse vector. And how do you prove this? Well, this is a theorem in one of my old papers. Indeed, this is, as I told you, when I started to think about this object, I didn't know. You are in the jungle, you are doing research. What do you know about the Poisson structure induced on Z? You know there exists a codimension 1 foliation. First thing I did was to compute the Gauss-Beyond class. If you know foliations, and I'm just talking to people who are already specialized in foliations, and we don't need this for the rest, but you know that Gauss-Beyond class, it gives you a good indication. And Gauss-Beyond class was 0, okay? But there are foliations with Gauss-Beyond class that are 0, which are 0, that do not satisfy this condition. For instance, a foliation that Raju mentioned the other day, which is called the red foliation. So you can ask many things, and I think that this is good, that is on the second list of problems, not in this first one. You can ask many things to a manifold. For instance, if you have a foliation, which is the red foliation, which is a foliation that you can define by planes inside your torus, and you can fill S3 with the red foliation somehow, because you have these two torus that give you the S3, and this is the common picture that you see, a red foliation. This guy here cannot be, never, the symplectic foliation. Induced. This is easy to prove with the things I will explain in 2 slides. Induced, indeed, I will mention exactly the theorem. Well, I mentioned as a theorem, but it's a proposition. It's very easy to prove. Red foliation cannot be the symplectic foliation induced on Z. So you have many natural questions, okay? But most of them, the answer is no. Because at the end of the day, it's very simple. We saw that the manifold Z is always a mapping torus. This is extremely easy manifold to describe. So you cannot have this kind of exquisite behavior that you can find in the wild world of foliation theory. Okay? Okay, so today I will answer this question. But the answer is yes. And to what extent this structure is unique means that I need to compare two Poisson structures. And this is going to be a magic thing going on today. This is very difficult to compare two symplectic structures. We have the path method. To compare two Poisson structures, the path method doesn't work. Why the path method doesn't work? Because the condition for the path method to work, which is something that we even don't think about in symplectic geometry, is that if you add up two symplectic forms, this is a symplectic form. Okay, if you take the path of symplectic form, this is a symplectic form. This is not true in Poisson geometry. If you add two bivector fields, and that's something that, well, I didn't think that I had to write so much, but I'm going to write it here. I should have added more words. I think that this is an important thing. If you take two bivector fields that are Poisson, this means that they satisfy the integrability equation given by the fact that the Schouten bracket is 0. What happens is that now I consider the sum of the two. Just the sum. Let it be if I take the linear path. Okay, I just take the sum. And I ask if the sum is Poisson. What I need to satisfy is this is 0. And then what I get by bilinearity is that this bracket given by pi 1 plus pi 2, pi 1 plus pi 2, you are going to get pi 1 plus pi 1 plus pi 2 plus pi 2 pi 1, which, by the way, is the same as pi 1 pi 2. Here there is a game of signs, plus pi 2 pi 2. So it's easy to see that, okay, even if this guy is 0, even if this guy is 0, because it's Poisson, and this guy is 0, still the sum is not necessarily 0. And this is an indicator that the path method of a tragedy, if you want, or you can think of this as a tragedy or not, or as something interesting, that the path method doesn't work in Poisson geometry. And this is not a secret. I mean, people in Poisson geometry have been trying to make the path method work. It doesn't. So you have essentially cohomological constructions that live in H1 to make the path method work. Even local.
Sorry, very stupid of me. Like pi 1 plus pi 2, pi 1 plus pi 2, the Schouten bracket. So pi 1 and pi 2 are 0 from the initial data.
No, yeah, this is what I was saying. Like, yeah, this is what I was saying, that this is a 3-vector field. This is not a 4-vector field. Pi 1, when you do, this is a 4-vector field. Yeah. So this is not antisymmetric.
Okay. So pi 1, pi 2 is not
pi 2. It would be antisymmetric if it was 1-vector field. It's a bivector field. It's like it's a whole jungle of signs that so now I should teach you. Indeed, I should teach you a course. It would be reasonable to have 1 hour in Poisson geometry in Poisson calculus. Okay, but why didn't I do this? Because okay, the message of the course is Poisson geometry is hard. Okay, but symplectic geometry is closer to symplectic geometry than to this jungle of Poisson geometry. So I didn't want to get so far into the jungle, but it's good to know that there is a jungle. Okay, so yeah, so the signs don't cancel out. That's the problem. Okay, now and for that I would need to teach you how they change the sign when you. And this is in a. I taught a course about this not so long ago in Germany, and I have the slides. But I thought that this is like I should take like 2 hours.
Maybe it depends on the degree of the form, and there is a
degree on the form, exactly.
And there is a whole business of L infinity algebra, blah blah. Maybe I'm not sure.
Exactly, it's the same. You are completely right. Okay. You may, if you have the model of L infinity algebras in your mind, it works a little bit the same.
Oh, okay.
Indeed, there are people who are a posteriori relating on the L infinity business with Poisson business, but it's a good intuition. There is a whole sign, okay? So you have degrees that change. So for bivector fields, it's not the same as vectors, exactly. That's a good model, the one you have in your mind. And it's a theorem that you can associate an L infinity algebra. There are people working on that point of view. I'm sorry that I am not an expert on L infinity algebras, but it's totally, you can think of that. It's a good intuition. Raju. Okay, where I am. Let's go. We have to prove all this, okay? We have to prove all this. And now, and that's important, this uniqueness is going to be given by equivalence of two of these Poisson structures in a neighborhood. But what I just showed you is that in general, the path method doesn't work for Poisson structures. So what are we going to do? Are we going to finish the course here? No. Let's prove that it works for B Poisson. That's fantastic. And then, for instance, once we know it proves for B Poisson, one thing we can do is to go to the first class where I proved equivalence of symplectic structures on manifolds, okay, on symplectic manifolds. And you remember that in the first class, what I said is that we can make the path method works, and the classification was given in terms of the RAM cohomology. This was for symplectic. Now the question is, can you classify B Poisson structures on a surface? How can you classify this? Well, this slide is what Olga Radko, as I said, Olga Radko unfortunately deceased last year. This is bad news. In her thesis, she classified these B Poisson structures on a surface. And what she found is a collection of invariants. When we say invariants, we mean different invariants give different classifications, give different classes in this classification. And what she proved is that the invariants are geometrical, so the topology of the surface and the topology of the curves where P vanishes. Remember that if I'm two-dimensional, a bisymplectic manifold is given just by a collection of curves. Okay. On my first slide, I said the other day, assume that it's oriented, as you will see in the class of Thursday. And indeed today also, because I will show some obstruction theorems from Gil Cavalcanti. Sometimes it's good to think that it's unorientable. But Olga Radko was also assuming that they were orientable. And then she found some dynamical classification. Attention, big surprise. The periods of the modular vector fields along gamma I. Gamma I are the critical sets. And then, of course, the modular vector field, what I have shown you, is that it's tangent to the critical set, because we have computed, and it's partial of x1. Therefore, it's tangent to the critical set, okay? And now I have a curve. I can compute, it's a periodic curve. I can compute the period of this vector field. Okay, the period is the time it takes to go back to the initial point. And I can do this for different connected components of the critical set, because, in the initial example, I had a sphere with the equator, but I can have different connected components. I can have 2, 3, etc. So she observed that this modular vector field that I just described gives you these examples. What I'm going to do today, indeed, is fascinating. I'm going to identify these modular vector fields as an invariant in cohomology. Okay? Okay, you already did this. It was the invariant in the first Poisson cohomology groups. Let me show you an easier cohomology. It's going to be a cohomology that looks very much as the RAM cohomology. It's the RAM cohomology adapted for bisymplectic manifolds. Another invariant that Radko found is the volume. Okay, the volume, you may think of it as the class. Okay, when you study the RAM cohomology, the integral is just the cohomology class, right? So you might think in cohomology class from the RAM point of view. And she observed something which is quite miraculous, okay? And doesn't work as well if you consider more sophisticated singularities. She observed that if you consider this volume, which she says, I take an epsilon neighborhood in a neighborhood of my singularity, okay? And I compute the area form of outside. Then she observed, okay, this area form, if I don't look at the south hemisphere, it's going to go to infinity because omega pi is the dual. So it's, here it will be 1 of h over dh d theta. So when h goes to 0, this volume goes to infinity, okay? And the south hemisphere, it goes to minus infinity. The magic that Olga Radko proves is that this limit, when epsilon goes to 0, of these volumes, which is, I'm going to do like my students, okay? They say plus infinity minus infinity, my engineer students, 0. No, it's not 0, but it's finite. And that's the magic of these singularities. Well, indeed, she did a descriptive description. She completely classified, and that's the argument. Today, what I'm going to do is to put this invariant inside a cohomology class. But I cannot wait any longer. I need to go on. Okay, I need to go on. And I need to introduce now. This is something I was waiting to do the other day. This is very important. What I'm going to do now is to change my glasses, okay? You see me here with these glasses, the ones that I use to write in my computer. But when you get old, you need a pair of 2 glasses, okay? If you are clever enough, then you may use some contact lenses attached. But there is a moment in your life in which you deny that you need to adapt. So you need 2 couple of glasses. You need some glasses. Okay, these are the horrible glasses. They are pink, okay, though they are pink, so they are nice. But with these glasses, I read close to me, okay? When I want to read a book close to me, I need these glasses. And when I want to look at you in the distance, from Barcelona to China, I use these other glasses. I need to change my glasses depending on what I want to see. And then, of course, you have progressive glasses, which is you get to them the day in which you accept that you are getting old. But before you're accepting that you get old, you play with these 2 glasses. Oh, I don't see you, I see you, blah, blah. So why I'm telling you about my glasses? Because what I'm going to do now is to change glasses to look at the Poisson structures. So what I want to say, I should have included more slides here, space for note. What I want to say, and that's the fundamental thing, no? I'm going to start with an example. I take this B Poisson. I don't like this color. I'm going to write magenta. Okay, good. Okay, oh, pi, well, never mind. I take this Poisson structure. This is a well-defined structure. This is a smooth Poisson. And now I dualize. I do this. Well, it doesn't matter what you do. This is not as smooth as the round form. Why? Because this is not as smooth when h equal to 0. You agree with me? It explodes. It goes to infinity. Okay, what I'm going to do now is to change my glasses. With these glasses, I just see a not as smooth the round form. So I change my other glasses. Wow! With these glasses, I see a completely different thing. Look what I see. I'm going to do the following. With these new glasses that I have, I can mark this here and call this DH bar. And then I have a perfectly defined form. Who is H bar? H bar is the logarithm of H. Well, but the logarithm of H is not a smooth function. But I tell to myself, okay, it's not a smooth function because you are thinking, okay, I need to change my glasses. I don't see. This is not a smooth function, okay? When I think of this as the RAM differential form, but maybe this is a smooth function if I change. When I say that something is a differential form, this guy, it's a section, okay, of a bundle. Which bundle? Nabla 2 cotangent of M. And this idea of identifying this new one form as a new differential H form, and then what I'm doing is to hide the singularity in the H bar, right? And this is like, if I don't look at the fact that this is a logarithm of H and I just declare H bar, this is a well-defined form. This is a smooth. But the trick is that it's a section. It is a section of a different bundle. And that's the whole story of what I'm going to do. Did you understand this? So what I'm doing here, it looks like I'm doing here something that is forbidden. But it's not forbidden as soon as I find that there is a theorem that tells me that I can do this, okay? And that's the magic. So the whole magic of this is that you can change your glasses and look at these B-Poisson structures as actual symplectic forms over a different, the thing is that this is not a section, it's a section, this is a section of Nabla 2 of a different bundle, which is called the B-tangent bundle. And this is what I'm going to explain now. Okay, so but essentially I'm going to explain you this formally, but essentially what I'm doing is this. Okay, is declaring this new guy a generator, as infinitesimal generator of something. Okay, let me go to this, and this is the most important thing. This is something that if you don't understand this, please ask me as many times as necessary, because this is the core of the class of today. So in order to do this thing of defining a new tangent bundle, in order to define the new cotangent bundle, I need to define a new tangent bundle. And I do this thanks to a theorem of Severance 1 that tell me the following. They tell me if I have a set of vector fields, and this set of vector fields are generating, or I get a set, okay? I get the set of B vector fields. These are the vector fields that are tangent to Z, are pointer Z. Of course, there could be vector fields that are not tangent. For instance, I could have a transverse vector field. This guy is not a B vector field. I want a guy who is a B vector field at points on Z, who is tangent. This is a B vector field. So I take an hypersurface and I take the set of vector fields which are tangent to this hypersurface. And this is something we can even write down in coordinates. Okay, let me write it for you. If I have a manifold of dimension 2n, and I take H an hypersurface given by H1, for instance, x1 equal to 0, I take this hypersurface, okay? So now I have, this is x1 equal to 0, okay? This is an hypersurface. Then the idea is, what is the expression of a B vector field? A vector field that I have a vector field, in general, a vector field has to be a sum of vectors of this type, right? I take some coordinate function, x1, x2n. That's a general vector field. And now I impose the condition that along Z, this vector field has to be tangent to Z. Okay, if it has to be tangent to Z, what does it mean? Well, I could have a vector field, okay, which has a term of time x1 times a function partial of x1 plus whatever functions of the other variables. So indeed, this I go to dimension 2n. What is very important is that I need the first component of this vector field has to be a product of x1 times f, because it has to vanish at x1 equal to 0. This means that the set of vector fields tangent to z is generated by the vector fields and here I have all the other vector fields. This is what this is telling me. And what it turns out is that if I look the set of vector fields generated by these vector fields, this is exactly the B vector fields. This is telling me that the set of B vector fields is a C infinity module, because it comes as multiplied by functions, which is finally generated. And I could say that it's a projective, even in the language, if I like algebraic geometry, that is a projective C infinity module finally generated. Fortunately, Serre and Swan, Serre in the analytic case and Swan for smooth bundles, they proved, okay, they proved that when you have such a thing, when you have a C infinity module finally generated, and this is what I proved for you, then there exists a vector bundle whose sections are precisely the B vector fields. And now you have to think, wait a minute, but this B vector field is not any manifold. No, it's not any vector field. No, it has to be tangent to several points on Z. And this makes these vector fields very special because they have to be generated by this. And this is equivalent, if you dualize this guy, to declare dx1 over x1 as new variable. This is totally equivalent, which is what I was doing in the example. Okay, so we apply the Serre-Swan theorem, and Serre-Swan theorem guarantees there exists a vector bundle that we call the B-tangent bundle. Why the B-tangent bundle? Because already Richard Melrose had used this notation. The B-tangent bundle is the vector bundle given by Serre-Swan theorem that tells me when I have a projective C infinitely generated module, okay, there exists a vector bundle whose sections are given by this module. Okay, so the B vector fields can be identified just as sections, and here I use the standard notation where gamma are sections in this neighborhood of this bundle. And these are exactly the B vector fields. And that's a magic moment, because once you have the tangent bundle, once you have this vector bundle, which is new, you can dualize. And then you get the B cotangent bundle, which is just the dual, because at every point this is a vector space, I have the right to dualize. And the magic moment is that now, instead of looking at the Poisson structures as B Poisson structures, as Poisson structures, you think of them as sections of this bundle. This makes them as differential forms. Indeed, as sections of this bundle when P equals 2. This means that when I write 1 over h dh over d theta, I can do this. Even if this is not a smooth the RAM form, this guy here, this is the d of h bar, this new one, this is the dual to the vector field, to the first generator of this C infinitely generated module. And that's fantastic, because then it means that I can consider something that are called B forms. But what are B forms in practice? Where a B form is a form that you can always write if you have fixed that your singular set is given by f equal to 0. And this is something very important. You can always write them as df over f, which alpha plus beta, where alpha and beta are the RAM forms. And that's something that is this the composition unique? No, but along Z is unique. So this decomposition, what it does for you is to understand what are these new forms? These sections of the bundle are not going to be smooth, but are under control, can only be of this type. F is the critical set, F equal to 0. This defines Z. F is what I call a defining function. And once I have this decomposition, I can go completely nuts, because look, one thing I can do is to define the differential of omega. Once I have this, let me change color because I don't like green to write on the screen. The differential of omega, I can define it as the differential of F over F, which alpha, I apply essentially Leibniz rule here, plus the differential of F over F, wedge differential of alpha, plus differential of beta. Okay, and this goes to 0. And therefore, this extends the RAM differential to this new complex. So what I have done for you, and this is the most important part of the course, is that I have extended the set of differential forms in order to make legal this kind of singularities. People here who come from algebraic geometry may identify this as the log complex. This is exactly the log complex in algebraic geometry. But when you look at as holomorphic forms, the cohomology computations are slightly different. It's an interesting one. And with this in our hands, we define a B-symplectic form as a symplectic form over this bundle. So you understand that now this change of glasses means that I may look as a B-Poisson structure with these glasses as a Poisson structure, and with these glasses, I may look at this as a B-symplectic structure, and it's the same. A B-symplectic form is just a symplectic form in the new complex. This means a closed non-degenerate B form of degree 2. And what's fascinating, why did I do this? I do this because I want to classify Poisson structures, okay? And for that, I need path method. And the path method works for this guy, for this class of Poisson structure, okay? So this allows to prove a Vidarbo theorem because the path method works. What's fantastic, what I'm telling you now, is that before, in the same way I told you that the sum of two Poisson structures is not Poisson, now the magic thing happens that this is indeed a form, again, that if I take the path, I mean, the path is going to work. I don't have the obstruction that I had before. I may have other obstructions. So, okay, this is something I already explained. So example, let me give you an example. If I give you an example, now I'm going to give you a B-symplectic form on T4 that comes from an extension. And this is where you see this decomposition that I'm doing here. This is the H, this is the D of the logarithm of the sinus of theta 4. And this is a legal, this form is not a smooth, the RAM form, but this form is a B form. And it's as smooth as a B form, and it's not as smooth as the RAM form. You see that it's not as smooth when you plug the logarithm of the sinus of theta 4. What's interesting about this structure, okay, is that this corresponds, this alpha here, this indeed has a lot of meaning if you analyze with this data here, what is the symplectic foliation on the critical set, then you get that the critical set is a torus of dimension 3, and that this symplectic foliation is the rational flow on this T3. So it's a very interesting example, and this is an example where we can extend globally to M. We can totally extend to the whole manifold. Now we want to understand what are the invariants? How do you measure the invariance? I mean, of course, if I have this B cohomology, first thing, can you compute this B cohomology? And there are two magic and important and fundamental results. The first one is that yes, you have a control of the B cohomology. if you have, if your M is your manifold and Z is the critical set, the B cohomology can be decomposed as a direct sum in degree K, the standard, the RAM cohomology. This is the RAM cohomology of your manifold. And here in degree K minus 1, that also are the RAM cohomology. How do you prove this theorem? This is due to Matteo and Melrose, and the proof is just an elaboration of this decomposition that we have to keep in mind, which is very convenient. And then this beta here is the class of beta and the class of alpha in this decomposition. Observe that if omega is a K form, then alpha is a K minus 1 form. And beta is a K form. This decomposition tells you I have some singularity, but I have it under control with this term. And then I have some the RAM forms. And thanks to this decomposition, we prove Matteo Melrose. Just by taking the class of alpha and beta, you can prove this theorem. Okay, what is the meaning of B cohomology? And that's what I want to say. The meaning of B cohomology is the classification of the B symplectic forms. And that's like, you know, that's a step on the moon. When we started to work on this thing, we had no clue, okay? What is the Poisson cohomology of this thing? I mean, Poisson cohomology, it's even not necessarily finite dimensional on a compact manifold. What I'm saying is true. Take, for instance, the zero Poisson structure. I'm going to leave you to think, I give this exercise for Raju to compute the Poisson cohomology in this case, for the zero Poisson structure. But here, the good news is that this new cohomology is isomorphic to the Poisson cohomology. That's a game changer in the theory of Poisson theory, because we had up to this moment when we proved this was in 2014. Well, that's not true. This was in 2010. But you know, you send a paper for publication, in the journal, they are not very quick, and then you get it accepted 3 years later, and then you get it published in 2014. But this was already in our archived version of this in 2010. Okay, so that's fantastic, because before this moment, only few classes of Poisson cohomology were able to be computed. The case of Lie algebra, for instance. That's a place where you can try to compute. If the Lie algebra is not semi-simple, you have some pain, okay? But in general, it's hard. In general, there are no formulas to compute Poisson cohomology. So this is fantastic. So this allows us to understand, indeed, some old results by Radko, for instance, to recover some old results by Radko that use Poisson cohomology. For instance, she computed Poisson cohomology by hand, and with this identification is a second. Because look, Poisson cohomology, you compute it as B cohomology, and B cohomology, you compute it from the RAM cohomology. This is an exercise. So indeed, this is another exercise for the second list, this corollary, the proof. Wow. Okay. Okay. Time to talk about obstruction theory. Obstruction theory gives me, what is obstruction theory? Obstruction theory be a cohomology. This means give me a manifold, I just look at the topology of the manifold, and I'm able to tell if this can admit a B symplectic form or not. There are several exercises in the list. I left you the other day to think about S4, and now I'm going to do a spoiler of the class of Thursday, because I'm going to give you the tools to solve these problems. First thing, we proved that if you have a compact B symplectic manifold, H1 doesn't have to be 0. Why? Because if H1 is 0, the surprise is that the symplectic foliation of Z would have a singularity, and this would lead to contradiction. And therefore, from Matteo Melrose, these are direct applications of Matteo Melrose. You get that H2 is different from 0. But you can also prove that H2 of Z has to be different from 0. And this tells you that the third cohomology group is different from 0. I'm going to tell you a secret. The fact this gives you as a corollary, this first theorem, indeed they are propositions. I put them theorem because, well, it's a nice characterization, but the proof is 2 lines. As a corollary of this, the rep foliation on T3 cannot be the symplectic foliation. It's a second to see this. The symplectic foliation on Z of a B symplectic B Poisson structure. So that's a whole interesting wall. More sophisticated things, because in this previous slide, proof is very simple, but more sophisticated things is now we don't fix that. In the previous slide, we were giving some characterization of the cohomology in terms of set. Now we don't fix it. Give me a manifold, you don't choose the critical set. Can you tell me if it will admit a symplectic? This comes from elaboration of this big cohomology. And you can prove this as an exercise, indeed. The first one, in practice, is you can find it in a paper of Marcoux and Osorno. This is 2 pages in the Journal of Symplectic Geometry. I think I attributed this to Marcoux and Osorno, yeah. But indeed, Cedric Holmes gave a shorter proof in his thesis that works also for higher order singularities, which indeed is, maybe this would be good to do it in the problem session. And the characterization is the following. With this, you can prove that on S4, these are 2 different theorems that give you 2 different proofs that S4 cannot admit any B symplectic form. That's an exercise in the list. It's exercise 1.6 with the new exercises that Pau has added. The numeration has changed, but the current list that it's uploaded, it's exercise 6. How do you prove this? This is very simple. Well, you prove that having a B symplectic form gives you a class in the second cohomology, which is non-vanishing, and such that Cn-1 is non-vanishing. In the case of the sphere, you apply this to n equal to 2, and this gives you just the existence of a 2 form. If you are on the sphere 2, we know that H2 of S4 is different from 0. But this is the theorem of Marcoux, Osorno, and Cedric would be telling you that there should be a class here, which is non-vanishing, contradiction. So I have proof for you in 1 second that S4 cannot admit a symplectic structure. You can also prove it with a more sophisticated theorem, that on a manifold, you can find classes A and B on H2, such that A to the n-1 times B is different from 0, and B is different from 0. When I don't say anything here, of course, I'm using the cap product. Okay, this is the cap product in cohomology. This is a bit more difficult to prove, but it's exercise 1.7 in the current list. Indeed, this table, it's a nice exercise that you could also check, which is a corollary. All this table can be obtained as a corollary of the second theorem. Well, the first one comes from the fact that the obstructions for a structure to be symplectic lie in H2. And here you have a table. If you are interested in, here you have I don't know if you see this, but here it's a connected sum with different orientation. If you have CP2 and you take several copies of CP2 with different orientation, it's to know when this admits a symplectic or a bisymplectic structure. Which here, I mean, I took this from the paper of Cavalcanti, and this is what he calls a log symplectic. So this is what we call obstruction theory, and you will need this to do the theorem. And the proof is playing with Matteo Melrose, really. It's very simple. Important things. Let's talk about the path method. Okay, we are at the end of the class, and it's very important to tell you that the path method works. So in particular, as a consequence of the path method, first thing we get is this theorem, which is the Vidarbo theorem. That comes as a surprise from the Weinstein-Splitting theorem that I told you the other day. This, okay. And then the most important thing is that we have several Moser theorem. The most important one is the one on this second. This theorem is the most important one that tells you that if you have a family that you need to assume it's a family of B symplectic forms, such that the cohomology B class does not depend on T, then there exists a family of diffeomorphisms such that leaves Z invariant and such that it satisfies this formula. How do you prove this theorem? It's the same proof. It's the same proof of that I did of the path method. Okay, you say that this class does not depend on T. It means that it's constant. So here you may try to compare omega 0 omega 1 minus omega 0 is the differential of beta, and here you put minus beta. It's the same proof, but what is the difference? That these guys now are B forms. And now I have to be elegant solving an equation on B forms. Okay? Why I know this equation has a unique solution? I know this because this is a B form, and I'm assuming that this is a path of symplectic B forms, therefore non-degenerate. Therefore, there exists a unique solution. How do you know that you can integrate the flow of T? Because the manifold is compact. And if my manifold is compact here, I don't say it, but this needs compactness. I can integrate the flow to wherever I want. Okay, of this guy, if I do the pullback of these guys, I get that this is omega 0. It's the same proof. And phi T, remember that it's just the T-dependent flow of this guy. Equal to T. Okay. Then I take the flow, so I take the solution to this differential equation and I integrate the flow. What I have used that is different. Well, I have just changed my glasses. Instead of differential forms, they are B forms. I don't care. The method works the same. Well, there are some subtleties. You have to extend the Lie derivative. Can you do this? Yes. I have already extended the differential forms. Oh, magic Cartan formulas work for B forms. Of course. Okay, and this is how you prove it. Okay, then you have to be careful, as I already said in my first class of the RAM, that of the path method, that if you apply the RAM method locally, the integration property, this is something I already said the first day, comes from the fact that you can assume that this guy vanishes at 0, and you can assume this because you can assume that the two forms are the same. Here in the notes, I have skipped, this is the most important, some other versions, preliminary versions of this result that are good enough, like this one, what I call the relative Moser path, that are good enough for the local or semi-local case. But with this one, you have all the other cases comprised. So application, let me give me an application of the RAM theorem. You can reprove Radko's theorem like a boss. Okay, because this condition that you have here, that the path method, you need to assume, if you are in any dimension, that you have a path, and you need to assume that this is a path of B symplectic forms. This was also happening in the symplectic case, but in dimension 2, you get it for free. For free, you get that if you have one class, then the path is a path of symplectic forms, because they are of maximal rank, and because of convexity of the linear combination, you get that this is also a path of B symplectic forms. So you make the same proof, and you don't need to assume that you have a path of symplectic forms. So in other words, in dimension 2, this theorem reads the following way. If you have two symplectic forms on an orientable compact surfaces, they are B-symplectomorphic if and only if the B cohomology class is the same. Well, this is our version of Radko theorem. I'm going to leave to the problem sessions. Wow, this is an interesting problem to add to the list, to identify these invariants. How do you identify? I'm going to tell you already that because of Matteo-Melrose, it's very easy to give an identification of, you say, the modular periods are going to be given by the classes on H1Z. And the regularized Liouville volume are going to be given by the classes on H2L. Okay, and via the Matteo-Melrose, you need to do look at this cohomology class, and then you know that this is H2, this is B cohomology, and this is the rank cohomology, direct sum, Matteo-Melrose, H1 of Z. Okay, and then, okay, and this is omega on the same class. This is the composition comes from looking at the decomposition in alpha and beta that I was already explained that you use for the proof of Matteo-Melrose. This is how you identify the invariants, okay? But let's leave this for the problem session. And well, look, the interesting thing is that this makes sense, right? With the fact that the Poisson cohomology, and this is something that it was a theorem, I already said, coincides with the B cohomology, because this classifies all Poisson structures. You use the B cohomology as a classification tool. And one thing you can do, and that's interesting, is to extend. I will not prove this, but this is a very wise application of the path method. With the path method, you can fix the critical set and find extensions. And then you have a control if they are equivalent or not using the modular class. This is something that I could, well, this is a theorem in our paper. And this is something that we could maybe include in the list of problems, but it's a bit hard. But well, the truth is that the proof is in the slides, but I will skip it. Just to finish, let me see where we are. We are in an interesting point, okay? We have these B-symplectic manifolds, and for the same price, which are forms of this kind, Y1 and here higher order terms. Okay, and now for the same price, I put here an M, and it works the same. We can define the same way the BM tangent class, and this is going to be, by the way, Pau, an exercise for the next list, not for Thursday, but for the last list, to check that you can construct the what is called the BM tangent bundle and the BM cotangent bundle. If you are one of these persons who like to classify bundles, you are in the good place, because Joaquin knows and has included a problem already in the list that you will see on Thursday, on to see if these guys are not necessarily diffeomorphic, I mean isomorphic as vector bundles to the standard cotangent bundle. Okay, and what measures this is the Euler class. Okay, so we have this class of structures, we have symplectic structure, and then we have folded symplectic structures, okay, that I didn't talk much about them, only the first day. But locally, I have to think that I have some local normal form of this type. And how are they different? I put them in different boxes of slightly different color. Are they the same? Well, one thing is that we already saw that we have a Vidarbo theorem for symplectic forms. This we saw in the first day. Today, we saw that we have a Vidarbo theorem for B-symplectic forms. And I will not prove it, but Martinet proved that there is a Vidarbo theorem for folded symplectic forms. Okay, something that I will mention next week is that we have the Elsanen convexity theorem. Well, I already mentioned this the first day, and for B-symplectic, we will see it next week. And we will also see that we have action angle coordinates. In the folded case, this is something we proved very recently with my student Robert Cardona, and this is a paper that is going to be published this week, just in time, at the EMRN, so you can look at it. And well, okay, you can try to play Sondel-San game. This is something that was largely studied by Victor Guillemín, Ana Canas da Silva, and Rita Pires, and Rita Pires wrote a wonderful thesis on the San theorem. So the question is in the air. Are we doing all the time the same and the same? Is this a deja vu? Are we now seeing that film in which every day we wake up on the same day? Well, not necessarily, because we have examples and counterexamples. If we have an orientable surface, for instance, this is everything you want. Symplectic, folded symplectic. And orientable or not is bisymplectic if you generalize this definition to non-orientable. You had this example of RP2, that beautiful example of RP2 that is in the list of problems. That was an example, my last example in last class. But in CP2, you know, this is symplectic, that this is folded symplectic, but it's not bisymplectic. This we know as an application of any of these former results. You may look at H2 of your manifold. That's enough. And S4, I told you, this is not symplectic. This is something we know because the class of the symplectic form has to be different from 0 on H2. We know it's not bisymplectic for the same reason because we proved this theorem indeed today. But is folded symplectic because any 4-dimensional manifold is folded symplectic. What a mess. So these manifolds are not at all the same. If you want to prove a result, you need to prove it for every manifold. However, I'm going to make a spoiler. There is a way to desingularize these singularities. And this is something we realized, and this explains many things. Why you can prove, for instance, a path method, why you can prove a Vidarbo theorem for all these forms. This explains. Indeed, they are all different boxes, but in a neighborhood of Z, they are on the same box. Because we can prove that in a neighborhood of Z, I mean, these are real global desingularization results. This is a result we did with Victor and Jonathan, that if you have an exponent that is even dimensional, this is something I had already said 2 days ago, then you can desingularize it to a symplectic form. Indeed, you have a family of symplectic forms that converge to your initial structure. But if it's odd dimensional, you can desingularize it to folded symplectic form. So today we have understood that one of these B-Poisson structures is, you can think of it as a singular form. But this singular form, you can also desingularize it. So you can think of it first with a pair of classes as Poisson structures or as forms, but you can also desingularize them. It means that they become folded symplectic structures. As a consequence, you inherit all the obstruction theory. So as any B2K symplectic manifold admits a symplectic structure, all the obstruction theory in symplectic geometry applies for B2 symplectic manifolds. Okay. Any B2K symplectic manifold admits a folded structure, but the converse is not true. An example of this is S4, which admits a folded symplectic structure, but no bisymplectic. That this admits a folded symplectic structure, it's a consequence of the H principle. Indeed, it's a theorem by Ana Canas da Silva that any 4-dimensional manifolds admits this thing. And generally, in higher dimensions, when you have something that is called stable, almost complex structure. Okay. And that's the end of my talk today. I will not explain, well, maybe next time I explain the proof, but essentially you have to take this song, and that's the way you have to think. You put things in boxes and you can transfer from these boxes. Now, natural questions. Can you prove results about periodic orbits, KAM, integrable systems, blah, blah, using this development? Not always. It's tricky. So in any case, that's the end of my talk, of my class. I went over time as every day, but okay, since I spent the first minutes of my class connected to my iPad, I think this is Fair enough. And I'm going to stop here. I'm very happy that I have the same people I start with. So this means that people could follow. I hope it was useful for you. And feel free to ask me any questions. Chung, do we have questions here?
Hi, actually, I already got a question. I mean, thanks for this very nice presentation of changing glasses. And I just want to make sure I get the idea correct. Is that when you say you have a form that has singularity and you want to switch it to something that looks smooth, not as the Lam form, but somehow as a new form. Can I say that the key point is that you changed actually the fiber bundle, and that fiber bundle should not be considered as naturally considered as a sub bundle of the original tangent bundle.
Exactly, that's very accurate. Indeed, if I had to say a metaphor of this thing, I'm going to put a metaphor that you will never forget. And I hope that the other people will never forget. Imagine that now somebody calls in your door and it's your friend, and your friend comes home to have dinner with you. Well, now in China, I don't know, to have a tea. Let's imagine that your friend comes home to have a tea, and you realize, you say, what a disaster. My house is a disaster. I need to order my house. There is an old trick. If you have a carpet at home, I don't have a carpet, which proves that my house is clean. You put everything that you could not clean under the carpet, okay? So the metaphor is the following. Here we have a singularity. The singularity is like the things that you want to hide from the person who enters the house. And you put the singularities, where do you put them? You cannot put them anywhere but on the fiber bundle. So you hide these singularities on the fiber bundle. And exactly, you don't need to think of this fiber bundle as a subbundle. It's the other way around, okay? Indeed, maybe not for this, not for tomorrow, because tomorrow we have, I say tomorrow and it's Thursday, sorry. I'm just thinking in terms of this course. This course, for me, this month of September, everything is this course. So on Thursday, already our plan is closed. We have a list of problems, but I think that it's very important that we include problems. There is a problem in the list number 2, where you see this, that you cannot think as it's not good to think of these bundles as compare them to the standard tangent bundle, because many people think, okay, you have a bundle and something very important. This bundle has the same rank. It's a bundle of rank n, but we know that 2 bundles of rank n, maybe they are not isomorphic, and that's the whole point. And what measures this, okay, if we were here like doing a class on characteristic classes, are precisely the characteristic classes. And indeed, with the Euler class, we have enough. But I think with Joachim, who now could not connect because in the mornings he's attending a class, Joachim is now by now an expert. You give him a bundle, and he can tell you if this can be isomorphic to a B-tangent bundle. So essentially, you have completely changed your bundle. You have to think your bundle as the carpet in your house, and you hide there what you don't want the others to see. You don't want to see the singularities. I hide it under the carpet. My friends are knocking in my door, and my house is a disaster. I hide it in the carpet. Well, I don't have a carpet, okay, but I have a wardrobe. And if you open the wardrobe, maybe everything falls on you. So you put what you don't want to see in this bundle. And you're right. We don't need to think, and it's very delicate to think about bundles as subbundles. It's not convenient because both are bundles of the same rank. Okay. So you can you have 2 different bundles over the same manifold, and you can have the same rank. And now you can compare them. Okay. And you have all characteristic classes to compare. For instance, an interesting question, okay, is like, do you have a Poincaré-Hopf theorem for this bundle? Is it the same? Can you use Masséna networks? All these are questions that are related indeed to the Euler class of a bundle. Indeed, we have, let's say, the tools to classify vector bundles are characteristic classes. And indeed, but they are complicated to compute, right? That's the problem. That's the whole problem. This is why in my opinion, the best place where characteristic classes and classifications are explained is in Mod 2. But if you want to compute it with your actual cotangent bundle, it's a bit mysterious. I have to confess that not much is written about this thing. Indeed, Joachim, I think it's the first person who started to attack these problems in his thesis. And indeed, as a heritage of having Joachim in the problem sessions, in the last problem sessions, I think we will include some of these problems. For instance, you may ask if something is parallelizable, if your initial cotangent bundle is parallelizable, maybe this is enough to guarantee that you have isomorphism or not. These kind of questions are the kind of natural questions. Yeah, exactly. So what you have said is the key point. Now we change the glasses. It's like we don't see the singularity, but the singularity is there, but it's hiding in the fiber bundle. So you don't see it as a coefficient of your local expression of the differential form, because it's hidden on the differential of x1. It's exactly this change of coordinates that I did. So I enlarged the class of admissible functions to include the logarithm, okay? And therefore, instead of looking at this as the differential of h over h, I look at the differential of the logarithm. And that's why I say, okay, the logarithm now it's as smooth as a function, okay, which I need to think as a function, as a section, zero section of a bundle. Why not? Let's think of in this term. Then as a zero section of that bundle, it's a smooth. It's not as smooth as a zero section of the standard RAM, of the one that you get. I mean, the zero forms will be functions, okay?
All right.
And that's why, and this is putting already on the table, and this will be fundamental to define, for instance, reduction that was mentioned today by Raju for this class, is to consider to put on the table this logarithm. And it's going to be important to consider this class of special functions that are not smooth, but we are somehow using them in the new bundle, and to define, for instance, instead of Hamiltonian actions, what we call big Hamiltonian actions, when we allow that the function is not smooth, but is in this complex of B forms.
All right.
Okay.
Yeah,
I don't know.
if
People, now you understand in Paris, I was explaining these things, but now you understand it better.
Thank you. Yeah, I think I see the idea better, but still a lot of details, I don't think I fully grasp them. I was looking forward to listen to Paul to teach me more during the tutorial class.
Exactly.
Yeah.
Exactly.
Okay,
Pau, Pau, you have to teach this. Okay, Pau, in the list that we have now, we have the slides that I used today. I already explained some of the abstractions theorems that they will use. One of them, it will be proved in the class, which is the one of Cavalcanti, okay, which is the hardest one. The other one has a very easy proof. You chose the difficult one, Pau, for the list. And yeah, but these characteristic classes for B cotangent bundle, there is just one problem in this list, the second problem, in which you ask yourself, for instance, there are many natural questions, right? If you have, now imagine that you have a torus, okay? Let me share again, computer, resurrect. Face ID doesn't recognize me. Your password is required. Today, everyone is asking me for my password. Okay, now I share a screen, iPhone, share. Mama. No. Today, my connection with my iPad is not so smooth, but now I have it here. I put it at notes. Okay, well, indeed, yeah. Let me. Well, maybe I had one leave comments. Here, space of notes. A space for notes. I forgot what I was going to say. What I was talking about. I wanted to make a picture Paul, remind me. I forgot. I lost what we were discussing.
You're talking about T2 torus.
Yeah, thank you. Thank you. Exactly. Thanks, Paul. I was going to give you an example of a torus. Now imagine that I make a torus should be magenta, okay? Now, an interesting question would be, take this torus, and I take this as critical set. Now, a question that I think that everyone here can already answer. Is this guy, can be this guy, can I define a B form, a B symplectic form here? Obviously, you can in a neighborhood of Z, but you can prove that this form will never extend. And the reason is the following. If you look at the sign of this Liouville volume of the form, let's say my B symplectic form is going to be symplectic away from Z. So it induces an area. So each time I cross a singularity, I cross a singular set. This changes sign. And then what I have is a volume form which is positive and negative. Contradiction. Why is this so? That in order to have a B symplectic form here, I need to have an even number of connected components. So to avoid this contradiction. And indeed, I had a student who completely classified all the BM symplectic forms, but what's very nice is that this form here admits a B2 symplectic form. And indeed, the fact that a surface admits or not a BM symplectic form depends on the corollary of the corollarability on if you can color a graph. Okay, and this I had a student who did this in the thesis with other many things. He did a fantastic thesis whose name is Arnaud Planas by him. And he did this in his thesis. So in particular, he completely classified BM symplectic forms on surface. And the first thing that he wondered is about existence.
Yeah. No.
Okay. We have a participant here. Okay, family moments. Okay, so exactly. So he completely, I mean, this is something we did together. We completely classified these VM structures on surfaces. And one interesting thing is the existence problem. So you ask yourself, I give you a picture and I give you Z, can you construct a B? This was an easy one, okay? And in general, you can have very different constructions. And the key point is that you can construct a graph. And the graph is the rep graph. The rep graph that you have associated to the, so the rep graph tells me that I take the rep graph associated to the symplectic foliation. Huh? So I take the critical set, I put it as a red line, okay, as a red line, red point, and then these guys, I put them as lines. And then depending on if this guy if this rep graph is colorable ability of this graph is what gives me the existence or not of this VM symplectic structure. So there are fun facts about this, and this is connected, of course, to the how is the VM tangent. Okay, and you will, I mean, this we will not see it as much. I mean, on Friday, on this Thursday, we will see something, but I think it will be not into Thursday. I think it's the 28th. It's a Tuesday where we have the other problem sessions. We will see more about cotangent bundles and these VM cotangent bundles. So
just a stupid remark, that is when you discuss this simple example on torus, you say that in B2 symplectic form it permits something like this. So can I understood it in a very stupid way that if I consider B2, then the form is like 1 over x squared, so you no longer have this cross sign.
exactly. That's the point.
Problem.
That's the whole point. And that's fantastic. So here I don't get this contradiction, okay, because here I don't change sign. Because I have the local expression has an even exponent. When I go from positive to negative, this does not change sign. That's the point.
Okay.
That's not.
Okay.
And well, there is a price to get to pay. That if you look at the Liouville volume, it goes to infinity.
Yes.
So you no longer have this thing that Radko proves. And I mean, and you can try to find some, indeed, some kind of interpretation of these volume formulas. These have an interpretation, interesting interpretation in terms of Duistermaat-Heckman. We wrote something like this in a paper with Victor, but we still didn't write the second part, which is the connection to Duistermaat-Heckman. And this is something that with Pau is in our list of things to do together with Victor and Jonathan, right? Pau has a long list of things to do. Each time is getting longer, longer, longer. So that's your interpretation is totally correct. You can also think in terms of the debloging, okay? If you singularize this object, then it becomes symplectic. And then you in the symplectic world, okay, you have the same sign everywhere of the, let's say the area form doesn't change sign. And the key point is on this torus, you change sign each time you cross the singular sign. This determines that you need to have an even number of connected components. So there are fun things around here. You can also play with a Klein bottle and so on. So yeah, I think that this is indeed quite easy to handle these examples because you can draw them, and if you can draw them, you can look at the change of signs, as you say. It's as simple as that.
Okay. Okay. Thank you.
Okay. Any more questions?
Eva, I have a question. In the Marcoux-Osno theorem, why m equal to 1, n equal to 1 case is excluded? There was a table, I remember from your slides, like there was a table. Yeah, exactly. So why m equal to 1, n equal to 1, that case is not there? Yeah,
well, no, this is, well, yeah, no. Yeah, you're right. That's a good point. And that's a good point. Thank you very much. N has to be, thank you. You're right.
N has to be greater than 1.
Yeah. Okay. N has to be greater than 1. You're right. It's the same. Otherwise, this still could make sense, but not with the proof that they provided.
Okay, because
but the proof is very easy. Let me tell you the proof of this theorem. It's so easy. Indeed, if you look to the paper of Marcoux and Osorio, you say 2 pages in Journal of Symplectic Geometry. That's a short proof, right? But if you go to thesis of Cedric, you find 2 paragraphs in his thesis. And the proof comes from the following observation. I think that sometimes it's good to explain proof to understand. This decomposition is key. Then you take the class of this beta. One interesting thing that I didn't explain because I cannot explain everything, but you have a property that this guy defines a volume form on Z. No, right. Well, this defines a volume form, in a neighborhood of Z everywhere. And this defines a volume form, alpha wedge beta n minus 1 on Z. Because these guys, you can think of them as putback from Z. This is something that we prove using the path method. So essentially, this class that you have is the class of beta. That this class cannot be 0, because if this is 0, then this wouldn't define a form. Well, first, this cannot vanish, but then how do you see that beta is different from 0? You can make a proof, which is quicker than the proof of Marcoux and Osorio. So attention, spoiler. And this is using just the Stokes theorem. That's how you prove it. So you have to understand that this comes from the class of this beta, and then when you remember what are the conditions. These other 2, it's a bit more sophisticated, and this is one that Pau will do in Thursday. The second, the proof of this theorem by Cavalcanti. This was problem 1.7. I don't know if we will have time, but we will. This afternoon we're going to discuss optimization for the class of Thursday. We have a meeting group of the people of the class. Yeah. You
Yeah, because
understand?
because m equal to 1, n equal to 1 case is known. I guess it is called del Peso surface.
Yeah, that's a good point. Yeah.
So I was
That's very
thinking maybe,
nice.
means there are some results. Say now, Minga,
Yeah.
there is a result by Brikov, and means I don't have the reference right now, but
yeah. That's a very interesting point. Like when
so
you are
I was
saying,
thinking,
that's a very nice example. So a nice first example are the Petrol surfaces. And these have become very popular in algebraic geometry, okay? The Petrol surface. And I will be able to give you very nice reference to this. And indeed, I found, like, for instance, Ping Chu, who is now in State College, he completely classified the cohomology of these Petrol surfaces. But then I told him, well, this was an old theorem. Then it's an interesting thing to compare his computations to the ones I gave. Now that you know that this is a V-symplectic struct, had meets a V-symplectic structure. Yeah, the Petrol surfaces are like I don't know, do they have also an important application in physics?
Because you can define Ricci flat metric on del Peso. So maybe there are way to, I'm not an expert, but I guess like there are some application even for the simple case, but it seems like Marcoux-Osno theorem doesn't apply for this special case, right?
Yeah, no, you are completely right. And this is an example indeed. This is a class of examples that I thought about it. That's something that we could, that's a good remark. Thank you very much, Raju. At the beginning, it was one of my star examples, the Petrol surfaces. You're right. Okay. Thank you. Thank you, everyone, for your patience. Raju, I still didn't get this. I asked these guys to give me the link to this talk because that talk is much better of my friend Marco Galtier. That talk is much more basic than the one that you showed me. And then he gave, let's say, a more sophisticated version in the mathematical physics conference, but this is not available. It should be available soon. In any case, they promised.
ICM is fine, but I never knew that ICMP in Geneva, yes, but I never knew that Marco talked in Rio symplectic geometry seminar. This is in Rio.
No,
this was Rio.
A conference. This was a conference in August. It was a 2-day conference, and he gave a talk about the same. It's let's say it's more or less the same slides, but my opinion is much more clear because
it was in IMPA. And it was in IMPA.
This was not in IMPA, unfortunately. It was in the Universidade. Well, you are in Brazil. This was organized by Graham Smith in the UFR in Rio. So I asked exactly. So maybe you can. I asked him, please, can you send me, because he did a YouTube transmission in direct, and then it has to be in YouTube once you have done the streamline. And I asked him what was the link, and I couldn't find it.
Thank you.
Yeah, so now my computer is connected. Okay, okay, thanks.
Okay, guys. Excuse me, Professor. I have a question. Maybe my question is a bit stupid. Omega pi is not small as h is equal to 0, but when we replace 1 over h dh with dh bar, it is smooth. So we can see it is smooth B form, yeah, right?
Exactly. You got it right. That's exactly what we are doing. So we are doing a change in which we say h bar equal to something that is not as smooth. And this is, if you want, is this legal? This is illegal, okay? But we are making it somehow legal. You are right. You are totally right.
I have another one.
Thanks that I see that you are one of the people who are following closer the course. And it's a pleasure to get your questions.
Thank you.
Maybe, by the way, I mean, if you feel brave enough, maybe you want to go and do one of the problems. What about doing one of the problems on Thursday? Do you feel brave enough to go on the blackboard?
If I have a chance.
Okay, yes, of course. You have a chance. Pau, do we give her a chance? Yeah, of course.
Yes, yes,
You
of
want to use
course.
the first exercise in the list.
Thank you. I have another
Well, I
one
mean,
question.
you can ask, of course, I mean, try to do it, and you can ask
I
us.
don't understand how the space Z pi L extends to a B-person structure on a neighborhood of V in M. Could you repeat it one more again for me? Thank you.
Yes, yes, exactly. Yeah, that was quick, huh? I mean, it was not you. Yeah, let me write it. Okay, that's, I mean, she's asking something that I went very quick. And this was because I wanted to get to the singularization, just to put, for you to have the general questions, the general picture, but I went too quick over that. You are right. Okay, so let me see if I'm able now do that. And now, okay, screen mirror, zoom. Yeah, that's indeed a theorem. I mean, I'm going to give you an example, okay? And then how we do this theorem in general. So what you are asking, indeed, here is an example, okay? So she's asking about the following, okay? And the question is a very natural question. We fix a codimension one foliation on something that a posteriori I want to make a critical set. How can I extend it in a neighborhood? That's the question that she's doing, okay?
Yeah.
And here I gave an example, and I think the example gives you a good intuition of how things can be in general, okay? This is an example of the equation that we get. And let me choose a different color. That is the way I extend it in this equation. What I do is to take, I have on the critical set, because I have this codimension one foliation, I have a co-symplectic structure, I have an alpha and a beta. Well, here alpha and omega, in this example, beta is omega. And then the only thing I need to do to extend in a neighborhood, I have to extend it, declaring just this, the differential of H bar, this one that I'm doing as a trick that has the singularity here. In general, I can think that this is of type dH over H, and H equal to 0 defines Z. So in a way, I have Z, I extend coordinates in a neighborhood. How do I do it? For instance, thinking that I take a tubular neighborhood. I take points at distance epsilon, okay?
Yeah.
And then the only thing I need to do is to plug here this one form and these two forms. How are these forms given associated to this structure? Well, they are given because, well, this is something that I explained quite quickly. It's true, but it's the same to have a codimension one symplectic foliation together with this transverse vector field that to have a pair of a one form and a two form, and such that the one form is closed and defines this foliation. This one form defines the foliation. So the kernel of alpha is defining the foliation, and alpha, it's a closed form. I can choose it closed. And beta is a two form, okay? And here, this gives me a good extension. What is the general extension? Yeah, this was the example, and the general extension is something I really skipped, almost skipped, because I'm always like, when I prepare the slides, I always put more than what I have. That's given by this theorem. This theorem in principle gives you a bit of a headache because you have a notation in terms of H1. Let's forget about this notation. Let me see, by the way, this is explaining me how I can choose alpha and beta from, how can I pass from the Poisson vector field transverse to Z to alpha and beta. And the way to do it, well, alpha or omega, and the way to do it is solving this differential form, these equations. This is one way. The solution is not unique, but this gives you a solution. So I need to look, if I have B, I have the vector field, I need to look for a 1 form such that it satisfies this condition and a 2 form that satisfies this condition. The other way around, if I have these 2 forms, I can determine these Poisson vector fields by solving these solutions in a way. And the most general formula that you are asking for comes suggested by that example. And this I have skipped. It's in the notes, but I didn't go quick enough. This is the most general thing that I do. F equal to 0 is the same as the critical set. Okay. And then the only thing I need to do is to think that I have Z, I need to define a projection in a neighborhood of Z. I need to define a projection that I call P. I could call it pi. This is a projection. This is a projection of my neighborhood, of the tubular neighborhood. So I take a manifold, I take a neighborhood of the manifold just as points at a certain distance epsilon. I take a small neighborhood. Okay, I call this the tubular neighborhood. Okay, and then I just project this neighborhood. I need to choose this projection. Okay, then if I have this alpha and omega, there I just choose that. In the former example, I extended trivially, but the most general equation would be by taking this pullback of this 1 form on Z, take the differential of F over F. Well, you can change the order. It doesn't matter that it's the first or the second term, plus the pullback of the other form. And that's the way you extend in a neighborhood. Okay. Then, I mean, the thing that I skipped, that's an interesting exercise and non-trivial, highly non-trivial. How do you see, if you take 2 different projections, are they going to give you equivalent forms? And the answer is yes, as long as this projection map, this is induced by the projection map, induces the same class in the first cohomology group. And this is again where the Poisson cohomology, which is isomorphic to the B cohomology, is telling you if 2 forms are equivalent or not. I said, I mean, but the main idea is it comes from the example. This is what you were asking, right?
Yes.
Okay, it's a bit more clear. I mean, you are right. You are right. It was not clear because I skipped these slides. But the good news is that you have all these slides because they are online. And well, this is indeed a nice application of the Moser theorem, totally non-trivial. Okay, so we will consider in the meeting that we have this afternoon, indeed a meeting that we have in 40 minutes with Pau and Joaquin, we will consider the possibility of adding this to the next list because, well, we need to think a little bit which kind of problems we put on the next list. We want to give more examples. So the Petrol should be there, the Petrol surface, and we'll try to put by your suggestion this also as problem.
Yes, thank you.
Thanks to you and for your participation. It's very nice to see that you are following, you are asking questions every day. And for me, this is important to know that people are following. For me, this is a pleasure indeed to get your questions, the questions of Raju, and any other question. More questions.
Hello, Professor. I'm interested in symplectic geometry. And could you recommend some books suitable for students who are new to symplectic geometry? Thank you.
Well, can you repeat? You are interested in mathematical outreach?
Symplectic geometry.
Ah, okay, okay. So, well, the book that I can recommend, I think, well, I would say when I studied And this I think my students will agree. We have some of my students, Anastasia is also connected. I think that the book by Ana Canas is a good book. What do you think? Lectures on Symplectic Geometry. I would recommend that book because it has many examples as motivating examples. There are other books. Then there is a book by Victor Guillemin, but I think it's harder to follow. Pau, like let's ask Anastasia and Pau. Do you have a specific recommendation?
Well, I would also recommend Ana Canas, and you can find it in PDF, so super easily on the internet. So
yeah,
she herself
so on her website,
yes,
on her website you can download this book. And if you are interested in aspects that come, for instance, I guess that Raju, that applies to Raju, that are closer to physics, then my recommendation is another book, but this is harder, called Non-Commutative, that she also wrote with Alan Weinstein. Non-commutative models in Poisson geometry or something like this. That's what my recommendation is, the book of Ana Canas to start with. And it's available online. So you can, I think I posted this on my website. Otherwise I will post the direct link, I think, right?
Oh, okay. Thanks for your recommendation.
Thank you. Okay, thank you very much for your attention. You're a great group. And I'm always going over time and you are still there. For me, this is passion. This is passion for mathematics. And Chung is also there. It's his morning. Okay, so well, I think that for today, that's it. I'm very much looking forward to you connecting on Thursday and to the class on Thursday. I mean, the class on Thursday, of course, I'm going to be there guiding, but I'm going to give the main role to Pau and Joachim. And I cannot wait for Thursday. I don't know about you, but I'm looking forward to it. So see you on Thursday, and don't hesitate to write me emails if you have questions. Thanks a lot for your participation. See you soon.
Thank you.
Bye, Chung. I couldn't connect, so